In this second part of our discussion of ionic compound nomenclature, I'd like to continue our discussion of how to name anions, looking at two additional groups of anions that I did not have an opportunity to talk about in the first part of this discussion of ionic compound nomenclature. So I would like to mention or point out that it is possible to take an anion and add hydrogen ion to it. Of course, the anions are negatively charged. They would attract a positively charged hydrogen. And when that positively charged hydrogen attaches to the anion, you make a new anion containing hydrogen that has a less negative charge. Let's take a look at this first example with the carbonate anion, CO3 minus 2. If you attach a hydrogen ion to it, you form a new anion containing both the carbonate ion and the hydrogen ion. Adding the -2 and the +1 charge together, you come up with a new -1 anion, less negative because it has been hydrogenated. It's containing, in this instance, one hydrogen ion. So you now have a new anion that you could incorporate into an ionic compound. And how would you name this new anion? You would call it the hydrogen carbonate ion, or if you look on your table of ions sheet, you'll see that there is an older name for this ion known as the bicarbonate ion. So hydrogen carbonate ion, bicarbonate ion, referring to the same species. And I remember many years ago when I was first learning about ionic compound nomenclature myself, I felt that a whole new world was beginning to open for me when I looked at products around the house, and all of a sudden when I looked at the ingredient label, the names meant something to me. So most individuals in their home have a yellow box that's called Arm & Hammer baking soda. And there's this big strong arm there on the cover of the box for an illustration. Well, if you look at the ingredients for baking soda, you'll find out that it's essentially pure sodium bicarbonate. And all of a sudden, you know, oh, I know what that is. I know that this compound contains the hydrogen carbonate, or as the baking soda box calls it by its older name, the bicarbonate ion in the ionic compound sodium bicarbonate. Let's take a look at this with another illustration involving the phosphate anion. So phosphate, PO4 minus 3, it can attach a hydrogen ion to it and it form a new anion, HPO4, with a -2 charge, less negative, because you've added a +1 hydrogen to it. Now notice the name here needs to include monohydrogen. We can't just call this hydrogen phosphate. We need to call it monohydrogen phosphate because this ion is able to rinse, repeat, pick up another hydrogen ion. So I'm taking monohydrogen phosphate, bringing it down here, and doing the same thing again, adding a second hydrogen ion to form H2PO4. This time, if you take the -2 and the +1 and add it together, you see that this anion has a -1 charge and goes by the name dihydrogen phosphate because we now have attached two hydrogen ions to make the substance, to make the anion. And we can do this one more time if we wanted to explore where we're going with this process and take dihydrogen phosphate and add one final hydrogen ion and form H3PO4, which is now a neutral compound. It is no longer an anion that would be part of an ionic compound. It's a neutral compound by itself, and we see that its formula begins with hydrogen, so we have an acid. This is how we recognize acid compounds. And the name of this acid is phosphoric acid, and we'll discuss in a later nomenclature segment how we name acid compounds. So the point that I'm trying to make here is kind of a sneak peek into what lies ahead. The way we generate an acid is to take a negatively charged anion and add the number of hydrogen ions necessary to take that negatively charged anion and form a neutral compound. So since phosphate has a -3 charge, we would have to add 3 hydrogen ions with a +1 charge to form the neutral compound phosphoric acid. So we can look at hydrogenated anions as a new set of anions that we can include in ionic compounds and in their nomenclature. Let's also take a look at the halogen oxyanions. These are oxyanions containing halogen elements. The most common halogen oxyanion are the oxyanions of chlorine. So if you take a look on your sheet, you're going to see ClO3-1 and ClO2-1. And as we talked in the previous segment on naming anions, we use the ate and the ite suffixes to distinguish them. Charge is staying the same. Chlorate, ClO3-1. Chlorite, same charge of -1, but 1 less oxygen, ClO2-1. But it turns out that the halogen oxyanions can form even more different types of oxyanions. So there also exists a ClO-1, same charge, but 1 less oxygen than chlorite has. So how do we name this new oxyanion of chlorine? And you see with my highlighting here, we are incorporating the prefix hypo, which means less. So hypochlorite has 1 less oxygen atom than chlorite does. Again, the prefix hypo meaning less. With that same sort of reasoning, we can go to the prefix per, which means more than or greater, above, and we see that the formula ClO4-1, 1 more oxygen atom than chlorate has with the same charge. We can attach the prefix per to the name chlorate and call ClO4-1 the perchlorate ion, 1 more oxygen than chlorate has. This same pattern is observed by both oxyanions of bromine and iodine. So I can come in and substitute out for the chlorine atom and put in either one of these halogens in its place. So I can write here BrO3-1, substituting chlorine with bromine, and then this anion, using the same naming pattern, would be called bromate. Here is the bromite anion. Here is the hypobromite anion. And then we can write the perbromate anion. So we can form a whole series of oxyanions involving bromine in combination with oxygen. Same formula and charge, just replacing the chlorine with the bromine and making the corollary change in the name as a result. And you can replace the bromine with iodine and come up with the iodine oxyanion series of, writing it down here, periodate, iodate, iodite, and then hypoiodite, the iodine oxyanion series. So that pretty much sums up the groupings that you see on the table of anions talking about, or table of ions talking about how to name anions. So we've just looked here at the right side of the sheet how we name anions. And now let's put the pieces together and look at some examples of naming ionic compounds. So in this left side, you see that I have given you chemical formulas for different ionic compounds. We can recognize that they are ionic compounds because we see that they begin with metal cations in combination with nonmetal anions. So how would we name them? Well, we name the cation first, followed by the anion. And doing a quick charge check, because we know that charges in ionic compounds, total charges of cations and anions, have to add up to 0. Magnesium +2 as a cation, chloride -1, and checking the charges, 2 times a -1 is a -2, and that adds to the +2 to give us a neutral compound. So we're good with charge. And we would name this ionic compound by naming the cation first, magnesium, and then the anion last, chloride. So looking at this, we have the correct name, the correct spelling for this first ionic compound. And you may want to pause for a moment and just see if you can complete the rest of this category and see how you do with coming up with the correctly spelled name and being able to present the cation name first, then the anion. You may want to pause and try this on your own. So picking up, hopefully you have filled in some answers here, and you're just going to compare with me and see if we agree on this nomenclature. I'm looking at the Cu copper symbol. I know that copper is a transition metal, and I see on the table of ions that it can exist with multiple positive charge states available. So I'm going to need to take a look at my anion first when I'm looking at a transition metal cation. The anion is going to tell me what the charge on that transition metal ion has to be. So SO4, I recognize the sulfate ion with a -2 charge. That means each copper in the compound has to be a +1 charge. 2 times the +1 is a +2, and that adds up with the -2 on sulfate to give a neutral compound. So I can name this compound copper, and I have to include that Roman numeral in parentheses indicating the charge per each copper ion in the compound, copper 1 sulfate. You could also use the older name cuprous sulfate to name this compound, but the older nomenclature system is not the preferred system for you to adopt for your own personal use. I want you to recognize it, but I want you to use the more current modern method, and the Roman numeral in parentheses with the name of the element is the preferred method for naming the compound. So copper 1 sulfate. Let's take a look at our next example, and I see that it contains the transition metal zinc, but recall that zinc is one of those rare exceptions as a transition metal. It only exists in compounds with a +2 charge. So when I name this compound, even though zinc is a transition metal, I do not want to include a Roman numeral 2 with the name of zinc. That implies that zinc can form a cation with a different positive charge, but it doesn't. So I see zinc cation present, and looking here, I'm trying to illustrate the use of the chlorite anion that we were just talking about. So chlorite having a -1 charge, and I see that these charges are adding up to 0, and I can name this compound zinc. Again, no Roman numeral attached to the zinc, zinc chlorite, naming the anion second. Let's take a look at our last example where you are writing the name if the formula has been provided for you. And I see my cation is a group 1A cation, a cesium cation. All group 1A cations have a +1 charge to them. And the anion is one of these anions where we have attached hydrogen, in this instance, to phosphate to form the monohydrogen phosphate anion with a -2 charge. So cesium +1, 2 times the +1 gives you a +2, and that balances the -2 on monohydrogen phosphate, and we can write the name for this compound as cesium. I think I might have to monohydrogen. It's not going to fit on one line here. Monohydrogen phosphate. So we have written the correctly spelled names for each one of the ionic compounds whose chemical formulas have been provided. But on a quiz or an exam, you could be asked to go in either direction. If the formula has been provided, you should be able to present the correctly spelled name. If you're given the name of the ionic compound, you should be able to write the correct chemical formula. So let's try it in the opposite direction. I see that my first substance is barium hydroxide. And you want to maybe pause for a moment and see whether or not you can write the correct chemical formulas for each one of these ionic compounds without having to look at the names and formulas on the table of ions to do so. So you need to make sure that you're putting these ion names and formulas in your memory so you can use them to do the nomenclature without the sheet in front of you. So looking at what we have here with our first example, barium hydroxide, I know that barium is an alkaline earth metal with a +2 charge. I know that hydroxide is an anion, and it falls in that exception category. It's a polyatomic anion, but its name ends in "ide." So that's a bit of a confusion. We like to think about anions that end in "ide" as monatomic anions, but hydroxide is a polyatomic anion whose name ends in "ide." So looking at the charges of these ions, I see right away that they do not add up to 0, which means that I'm going to have to use 2 hydroxide ions for every 1 barium ion present in the compound. This is a good time to remind ourselves that all ionic compound formulas are empirical formulas, simplest whole number ratios. So when we look at the compound barium hydroxide, it's a huge array where we have a ratio of 2 hydroxide ions for every 1 barium ion present in the compound. Simplest whole number ratio. And once I've used these charges to make sure that I have an overall neutral compound, it's a good idea to erase them. They're kind of like the introductory training wheels, so to speak, we used to figure out this formula, but now they're no longer needed, so I'll remove them when I present the formula for the compound. Let's take a look at the next example, iron 3 acetate. Now you just have to know, and the first name, the cation name, is pretty easy, indicating This is the iron ion with a +3 charge. Okay? Very useful to have that Roman numeral in parentheses to indicate the charge on the ion. The acetate is a little trickier. You need to have memorized that acetate has the formula C2H3O2 -1. And there's no way to reason it out. You just have to memorize that is the formula for the acetate and the correct charge. Okay, again I see that the +3 and the -1 are not adding up to 0. So I'm going to have to use 3 acetate ions to achieve a total charge of 0 overall for this formula. So the +3 of the iron 3 ion is adding up with the 3 times -1 for the acetate ion to give us an overall charge of 0. Now looking at potassium peroxide, potassium, an alkali metal with a +1 charge, peroxide, a polyatomic anion, O2, with a -2 charge overall. And again, these charges are not adding up to 0. Right? So it's clear that we need to use 2 potassium ions for every peroxide ion in order to have a total charge equal to 0. And once we figured that out, we can remove the charges and kind of clean up the name a little bit. And let me go back and do that for the previous example. Makes it look a little cleaner. So potassium peroxide, K2O2. The last example that I have up here on the board is ammonium sulfate. Ammonium is that unusual cation that is not a metal cation, and it has the formula NH4 with a +1 charge. Sulfite is SO3 with a -2 charge. So it is the partner to the sulfate anion, same charge, 1 less oxygen. Again, those charges are not adding up to 0, so I'm going to need to put a parentheses around the ammonium ion and have 2 ammonium ions present in the compound for every sulfite ion that is present. So the chemical formula for ammonium sulfate, simplest whole number ratio, removing these charges now that we've figured out what the formula is NH4 parentheses 2, subscript 2, SO3. And before I leave, let's maybe squeeze in here one last example. Let's see if we can't write the correct formula for the compound aluminum carbonate. So let's squeeze one more example in. Aluminum carbonate. And looking at this name, I know that the aluminum ion has a symbol of Al with a +3 charge to it. Carbonate, we were just looking at carbonate when we began this discussion. CO3 with a -2 charge. So looking at these 2 charges, I see that I'm going to have to use 2 aluminums for every carbonate ion present. 2 aluminums for every carbonate, Al2 parentheses CO3, 2 aluminum ions for every 3 carbonate ions present will give us a total of a +6 and a -6 that when we add together, we get 0. So the formula of aluminum carbonate, Al2CO3, looks a little crowded here to me. Let's try that again. CO3 parentheses 3, the formula for aluminum carbonate.